Hello, welcome to week 4, binomial probability and normal probability distributions. Okay, so what we want to be able to do with with these chapters is forecast happening events. So what are the chances of something happening? Maybe understanding the successes or failures of outcomes, but also predicting the probability of future outcomes. So there's three types of distributions that are in this PowerPoint, but we're actually going to only go over the first two, which is binomial distributions and normal distributions, primarily because the third one is not very emphasized moving forward. So, random variables. It's important to have that everything is randomized in this. So remember that we have two types of randomization. We have discrete and continuous random variables. Last week we discussed discrete random variables, which was the probability mass function. And in this example that we have right here, this is what we did in class, as well as we discussed in the video, was the 4 patients. So it was, for instance, what is the probability of 2 people out of 4 who take a certain procedure that has a 75% success rate. And just based on this, we know that it is 21%. This whole times 1, don't let that throw you off. That's basically geometry within our graphs to accurately read things. So in other words, these sort of graphs should be properly at the proper aspect ratio. So they're not skewed, they're not like stretched or anything. But that's nothing that we're fully emphasizing, but it is something to note. Okay. Now, when we're looking at probability mass functions, PMFs, there is there's a series of things. Let's just go through this. A family of probability models that apply to random variables in which there are a certain number of independent observations. And each of those observations can be characterized as a success or failure. So everything is very dichotomous. It's either yes or no, success, failure. And within that, there are the parameters. So the parameters are what is within that, the parameters of the situation. So n is going to be the number of observations, and p is the probability of success. So we'll be using p as well as a q. We'll learn what that is here in a second. Not sure why that was so slow, that last one. All right. So in order to calculate a probability, a binomial probability, there's a few things to look at. And basically what we're looking at is just what is the randomization, like how many chances of something is going to happen. And within this formula, we have kind of 3 distinct parts. First, we have the binomial coefficient, and that is going to be this right here. And so that must be solved, as well as the probability of success. So here's our p, and we have an exponent up there of x, and it's going to be the same x as this one. So we have an x here, we have an x here, and even on the q we have an x. And so q is the probability of failure. So it is the complement to the p, which is q to the n minus x power. And we will practice all of these. But first, let's start off with the binomial coefficient. So for this, let's just look at what this formula is right here. So we have an n and a factorial function. So that'll be on the next slide, but let's just look at what that actually is right here. And that is n explanation point, and it's going to teeter off into more numbers, as well as the x times the n minus x, and as well as we are looking at the factorial function there. So if this is throwing you off, let me just say out what it is. A binomial coefficient counts the certain ways of group items. A binomial coefficient equals the number of combinations. So let that capital C be the combinations of x items that can be selected from a set of n items. So in this example, we're looking at that there are 6 ways, and this is after you calculate it, there are 6 ways to choose 2 items out of 4. So you kind of start off as, what is the combination, how many combinations are there when you have 2 items out of 4? And that's what we have right here. All right, maybe I'm just having fun with this pen. Okay, so when we look at the factorial function, what this is, and this was maybe in high school, maybe you had it. So let's just say that this 4, actually let's just add it, I think it's on the next, there we go. Okay, so let's look at this 4. What does this actually equal to? It's not just 4. Well, actually it is 4, and then you count down and you times it by whatever is being counted down. So 4 times 3 times 2 times 1, and it actually equals 24. So that's going to be up here at the top. We do the exact same thing, we just plug and play whatever this x is. So this x right here is going to be 2, and so that would be 2 times 1, so that still equals 2. And then we do n minus x, so that's 4 minus 2, and that's going to be just simply 2 minus, it's going to be 2. And we're going to do the factorial function of that as well, which is counting down. So when we fully grasp this, what we have is 4 times 3 times 2 times 1, 4 times over 2 times 1 times 2 times 1. So this down here is going to be just 2 times 2, right? But there are a couple of little shortcuts here, what we have. And that is going to be, let me make sure that I'm doing this right. So what you can do, 4 times 3, yep. Okay, so when this is here, you can actually cancel out what if there's any matching pairs. So in this case, I can cross this one out and I can cross this one out. I can cross this one out and I can cross this one out. I can't do the same thing for these because these are still, these have already been crossed out. So what we really have is 4 times 3 over 2. So if we do that, that is 12 over 2. And that equals 6. Sorry, that is a horrible equal sign, but you get the idea. So with this heads, that's what we want in this. We have, this means that within this example, this means that you have 0 heads out of the 5 flips. So they all went tails. There's only one possibility out of the 32 that you get no heads. So this overall, am I able to do it? There we go. If I was to plug all of this in, it would actually equal just to that 1. So there's only 1 out of the 32 possibilities. Okay, so when we look at this, we can basically, this is one way to do it, is to calculate all this out. But the way that I was taught as well is you can just cross that out, cross that out, cross that out, cross that out, and look at that. You are left with technically a 1 on top, and that is still 1. 1 divided by 1 is 1. Okay, so there's only one scenario in which you can get 0 heads out of 5 flips. There you go. All right, so our next one is, what is our chances of flipping only 1 heads out of 5 flips? Okay, so you can do the math, you can have fun with this, but let's just find out what it is. So out of the 32, there are 5 scenarios in which you will get 1 heads out of the 5 flips. Okay, so what about for 2 heads? What is the chances of that? Well, it's 10. So you can also think of this as fractions with these numbers right here, because in the prior slide it was 1, right? Because there was only one chance, or there was only one scenario in which there were 0 heads out of 5 flips, and we have 5, and we have 10. So we're going to keep on building up. We're going to have another 10. So if I was to count that up, that would be 16, and then we have on this last one we have 5. That should equal, yeah. Oh, we have one more. Okay, that's right. Okay, so these are doing the exact same thing, so let's just give it a shot. So I'm going to cross this one out, and I can cross this one out, and that's all I can do here. Let's see if it's still 10. So 5 times 4 is going to be 20, 5, 10, 15, 20, divided by 2, that's 10. Alrighty, we are good to go. So this is like a kind of a little longer way, but you know, that it's maths. There's always a way. All right, lastly, what are the chances of getting 5 heads out of 5 flips? How many scenarios are there? Well, pew, it's back to 1. All right, so we can look at this as another way of what is this 32 over here? Okay, so this is 1. This is 1 chance out of 32. If I go back to these prior slides, what we have here is 5 plus 10, so that's 15 plus that last one, which is 16, and then plus 10, 26, plus 5, 31, and plus 1, we have 32. So we basically were able to find all of the different combinations or the different scenarios in which you wanted to find out how many times you flip a coin and move forward. How many times you flip a coin and see what how many scenarios there are. So let's go a little bit further with a binomial coefficient calculation. So a treatment has been successful 75% of the time. What is the probability of patients responding successfully to the treatment? What about 0 patients, 1 patient, 2 patient, 3 patient, 4? This might sound familiar because this is what we have talked about multiple times now. So what is the probability of observing 0 successes under these circumstances? So if we were to look at this C here, what would we have here? Okay. We have this part right here is going to be this part right here. And we can continue on with it by looking right here. So it's the factorial function of 4 over 4. What that ends up being is just 1. Okay, so let me change colors. So then we have the probability of success. So in this case, it would be, you know, the number of successful patients that survived the procedure. Okay, so it's right here. And we have 0.75 to the 0 power. We have 0.5 to the 7 power here. And we have 1 right there. Okay, and lastly, what we have, let's do blue. Is there blue? Yeah, there is blue. Okay, we have the number of failures. And so we have 0.25 to the 4 minus 0 power. And that's going to be right here. And that is 0.0039. And so, what is the probability of observing 0 successes out of the 4 patients? The answer is very darn small, 0.0039 or 0.3%. Okay, so we started off with the 0 successes, and then we can move up to what about 1 success? What is the probability of having at least 1 patient survive? It is a 4%. I'm just going to skip through this real quick because we've already gone through this actually with the PMF. Remember how I mentioned though that you can still, as a continuous variable, can still be in a discrete world, especially in this example. So here we are again with 3 successes, with 4 successes, and here it is the PMF in all of its glory. This is the area under the curve, and just by me looking at this, I know that we are looking at the number, or at least 3 the cumulative probability of 3 successes, and so basically we're adding this. All right. With cumulative, basically what this is we are adding all of these up and they equal to 1. This goes back to our original, basically our principles in probability or laws within that. You know, all of these numbers, all these possibilities, scenarios have to equal to 1 or 100%. So here, excuse me, I didn't always forget about these. You can look further into those if you'd like. So I'm going to go on. All right, so now we're at a good stopping point because I want to just show something, because we did all these equations, all this fun math, right? But there's also something else that I'd like to show you, and that is the internet. Okay, and with the internet, Well, I just wanted to show that we can do all these calculations very quickly. Okay, so let's just look at our example that we just looked at. There are 4 patients. The probability of success is 0.75. And let's just say, what is the probability of equaling exactly 2 successes? So 2 patients survive out of the 4, and that is 21%. We can go back here, and we can actually look at that too. Right here, 21%. There it is, yay. Okay, what about 0 surviving? 0.00391. We have 0.0039. Wonderful. Okay, now let's just play around with this. Let's just see what happens. So we're looking at what is the probability of x being of successes, whatever we put here. So let's just say greater than or less than or equal to 3. So if I hit enter, this is looking at everything to the left of after the third. Sorry, let me try that again. This is looking at everything from 3, 2, and 1, probability of success. So it's actually accumulating these right here. And if we look here, 42%. That's it right here. There it is. So this is the cumulative. So this is exactly what we typed in here. P, the probability of x being less than or equal to 3 is 68%. What do we have right here? 68%. Voila, the power of the internet. So that's why when we spend time doing these formulas, it's good practice, but it's also something, if you know what to plug in, if you have the idea here, then the internet can do wonders for you. Okay, so let me fix this. Alrighty, I'm not sure how that got off. Okay. So let's move on to the expected value and the mean of a binomial PMF as its balancing point, as well as the variance, which is its spread. So this, remember that this symbol right here is mu, and this is the population mean. And the way you find that is you multiply your n times your probability of success. And your variance is going to be n times p times q. So let's move a little bit forward with this. So with our 4 patients, what do we have? What is our mu? What we have here is n, so we have 4 patients times the probability of success, which is 3. So it's basically saying, like, on average, like 3 people survive this, which makes sense when you look at it as 75% out of 100, that's 3/4. And we have our variance, which is n times p times q. So we're looking at the number of patients times the number of success times the number of failure, and we have 0.75. Let's just add that little graph there. Voila, that's what we're looking at here, the number of successes. So although, again, this is a discrete thing, you can still have a mean that basically finds the balancing point for this data set. We will have some fun in class. Alrighty. We're gonna do activities because we're gonna have fun. All right, random variables. So we have 2 types, correct? What we just went through was the discrete random variable, just to kind of like overall summarize a little bit more within a binomial. So binomial, we're looking at x number of successes out of n. All right, so now, or n successes out of x. All right, so now we're moving on to continuous random variable. All right, we're finally here. We're having fun. This is great. So with this is where we get the probability density function, or PDF, and this is a normal bell curve and with an area under the curve. So in this case, we are looking at the age of anything, of any person 9 or younger. So within this, you can see on the graphs that continuous variables include everything in between, but this actually happens to not be. The area under the curve is just a way for us to identify our probabilities. We want to identify this particular area under the curve. So anything less than 9. So how would I write this out? What I would write is the probability of the years. I'm just putting Y. It could be years. It could be a coconut. I don't know. But it should be something at least that you know what it is less than 9. Voila. All right. Now remember that this whole area under this is equal to 1. Just wanted to put that out there because it's right there. I almost forgot it. Okay, PDFs obey certain rules of probability, and they can come in different shapes. We've already been through that. Almost everything we do in inferential statistics, which is making inferences, is to some degree based on a normal distribution. So this is how we move forward with things in data sets that are found normal. So it's important to know that there are different ways that you can look at it. So we talked about how this is a continuous. You can look at the exact same histogram, and basically you are dividing the students by age, or that could be just children. I don't know if they're students. So this is just showing the darker parts of the histogram correspond with all ages less than or equal to 9. So that's approximately 40% of the observations. All right, this is the exact same thing. So if you remove the histogram, you still have that gray area. It also corresponds with the ages that are specified. So yeah, this is the area under the curve. Okay, so within parameters and standard deviations. So let's again go back to this mu symbol, which is the mean, and this is based on population parameter. So you only use mu when it's population, and you use x bar when it is a sample. And then we are going to use this sigma for standard deviation. That's also the spread. And so let's just continue on with so if we, well, this is a notation, and this is something that usually is in your book or whenever it has a problem. But we have here is this is distributed with this little, it's a tilde, and this is the total number of n, what we have here, or the total number of n, and then we have the mean. Excuse me, that's what I meant to say. So we have the mean right here, so the mu, and then our standard deviation right here. Okay, so this is a great way when you are comparing different means, and maybe you put them on a certain scale down here, and you can better tell how much one is greater than the other just based on the means. Now, however, when you do this, this usually has to, if they shift on this horizontal axis, ideally in this imagination world, they are the exact same population, from the same population, and they have a perfect bell curve. So this is two different means, how you can see it. So we could say this is the average age of a collection of individuals. This could be the age of 20. This could be the age of 30. And so your means vary, and so you have some overlap on this. With normal distributions and different standard deviations, well, here we have that the first standard deviation. So these are two different populations. Say we just take an average of 30-year-olds from two different groups, right? And so the first one actually has a greater variance. So they have, within the observation, people who are much younger and people who are much older than the average age of 30. There's a horrible 3 and a horrible 0. I'm sorry. Whereas with this sample 2, it still has the exact same mean as 30, but there might not be such a variance, a deviation from the mean because it's much closer, as you can see just visually here. It means this is also the frequency is higher within that 30 range. There's the point of inflection. It's in your book. It's nothing that I've really sought out, but just pointed it out. You can move forward. Okay, so just as a reminder that this x bar is a sample mean, and this lowercase s is a sample standard deviation, in contrast to the mu and the sigma. We talked about this week 2, and I just barely brought it up, but we're going to dive further into it now. So within this perfect bell curve, you have a 68% that falls under the first standard deviation. We have a 95 under 2 standard deviations, and we have 99.7 in 3 standard deviations. Let's see what that looks like. So within this normal curve, we have right down the middle, this has to be symmetrical in this perfect world, that if you go out 1 standard deviation, let's just add it, and there will be more visuals of this, so I might be repeating myself, I'm sorry. This right here and this right here is 68%, and it goes right down the middle. So you have right here, this is 1 standard deviation above the mean, this is 1 standard deviation below the mean. And then it goes on to 95%, reaches all the way out here, and that's 2 standard deviation above the mean. And this is 2 standard deviation below the mean. This one's negative, or 3 standard deviations below the mean, and this one is 3 standard deviations above. All right, let's take another example. So the male height is approximately 70, let's say centimeters high. Let's just go with centimeters on this one because it doesn't actually say, with a standard deviation of 2.8. So with that, we could actually make our lovely bell curve and then put the average as 70, and then we would plus 2.8 to 70, so 72.8 is 1 standard deviation above the mean. We would also, if we wanted to know below, we would do 70 minus 2.8, which is 67.2. So it's good to know, again, this is where the symmetry comes in. This is where a perfect bell curve is exactly what we want for the answers we're looking for. So many random variables encountered in nature are not normal. However, we can often make variables more normal by re-expressing them in this mathematical transformation. So that's another way of saying this is like the imagination land within math, because it still follows some rules that work well when it comes to statistics. So we often need to know the probabilities of normal values that might not fall exactly at +1 standard deviation or -1, but it gives us a good boundary to know. You could almost say visualization. It kind of puts on some goggles. You have some familiarity with some depth, if I may. Let's move on to this. With a standard deviation of 1, say the mean is 0, imagine that we have one observation that is 1 standard deviation from the mean. If we want to know what is the probability of one observation being between 0 and 1 standard deviation from the mean, we would look up that from the back of the book and value it at 34%. So again, this is just showing you that since the bell curve is symmetrical and we know everything is perfect in this lovely world, that it is 68% and half of that is 34. Okay, 68. Seemed like a lot of slides. There we go. All right, there's our lovely formula. So our z-score is going to be whatever value we have minus the mean over the standard deviation. So let's go a little bit further with this. So now a common z-score is 1.96 as well as negative 1.96, and that is a z-score right here. So this negative 1.96 is a z-score. Ha 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 ha. All right. And so we know that half of 95%, well, we might not know it, but half of 95% is 47.5. I want to make assumptions. 95%, meaning that what do we have on the outside? We have these little choppy 2.5 percenters on both sides. There it is again in all of its glory. There's a lot of examples in this. I'm sorry, I always think like maybe more is better, but at this point I'm like, oh, that's a lot. All right, we'll be practicing some of the z-scores and standard deviations in class. All right, but now we're determining the normal probabilities, and there is a technique in which we want to move forward with when it comes to this. So first we must state the problem, and then we standardize the value of, in other words, we find the z-score, and then we'll sketch and shape the probability area within that curve, and then we'll use table B to determine the probability of it. So we'll go further. We'll just show you. Okay, so we want to determine the percentage of human gestations that are less than 40 weeks in length. So we know that an uncommon complicated pregnancy from conception at birth is normally distributed at 39 weeks. In other words, the population mean is 39. And the standard deviation of that 39 weeks is 2 weeks. So let X represent the human gestational length. So we have 39 weeks average, and we have 2 standard deviation, or 2 weeks as a standard deviation. Statement of the problem is, what is the probability that blank of the gestation is less than 40 weeks? So let's get to a visual of this. Okay, so this is a little bit better. So we need to find the z-score. So this is, did I skip step 2? All right, step 2, if we're standardizing the value, basically we're just plugging in the x and the mu and the standard deviation to go into the back of the book and look at the z. So what that looks like is 40. So we wanted to know everything less than 40 weeks of gestation. And so we do 40 minus 39, because that's the mean, over the standard deviation of 2, and that is 0.5. So what is this saying to us? Let's just look at this in a fun little way, just because I felt like put it on graph paper. Okay, so we have a standard deviation, right? Or a mean of 39 right here, and we are looking at this. So it's not one full standard deviation. It's actually halfway, because remember our standard deviation is 2. This would be 41 weeks. This is 39 weeks. We're looking at that 40, and we're looking at the area under the curve, which is all right here. So when you look at the back of the book, so what you do is once you find that z-score, you are going to find, so right here we have 0.5. So if I go into the back of the book, I will look up 0.5. Whoop. Now, because it is just 0.5, not 0.51, we wouldn't go any further. It is just 0.5, and so we now know that the possibility or the probability of gestation at 40 weeks or less is almost 70%. Whereas the probability of giving birth after 40 weeks, that's a 30% chance. All right, so this is it going a little bit further with it. That z-score. And this is the hard part where, you know, we mentioned about rounding, because sometimes you just need to go two spots after the decimal, but for a z-score, you always go 4. So just when in doubt, go 4. All right, so this is everything I just explained, but with more words. Maybe I had more words. I don't know. All right, we'll give this a practice here in class. We'll give another spot. We'll give another example. Okay, so what about births that occurred before 35 weeks of gestation? So it's the same amount of, we know that everything is normal. See, and this is one thing that the book will be kind of practice with, is that it will always say it's a normal distribution. If it didn't say that, then we really couldn't go further with these types of formulas. We could, but it's kind of assuming that it's normal because that's what everything is based on. So we're looking at, what is the probability of gestation being? Oh, we're looking at between 35 and 40 weeks. Okay, so that's really what we just wanted to get to. This is just extra fluff. So what is the probability of gestation being between 35 and 40 weeks? All right, so first we need to find the z-scores. We find it for both the 35 as well as the 40 weeks. So it's just right here, 35 minus 39 over 2. That is -2 and 0.5. So we already know this one, right? But we still need to look the -2 up in the back of the book. All right, this is my horrible example, but don't worry, there's visuals. So if we look up just -2 in the back of the book, notice that there's the negative sign. And we come over here and it is 0.0228. And then we know that the 40, and so what this number corresponds with, this one right here, is this spot right here at 35 weeks. Whereas this 0.69 is 40 weeks. And because we are wanting to know everything right in this beautiful green. Okay, so how do we find this out? Well, we found out that this little area right here, if we go back, we got from this number. So we know that from this information that if we move it twice, that 2.2% of individuals have children less than 35 weeks. That's what this fill-in is right here. So if we move over here, we are taking the 40 weeks right here, and we are subtracting the 35 weeks, so this whole area right here, to know what is in between. So that is 0.6915 minus 0.0228. So what does this mean? It means that about 66.87%, or 2/3 of gestations, fall in the range of 35 and 40 weeks. So 67% of individuals have children between 35 and 40 weeks. All right, so we state the problem. If we want to find the corresponding to normal probabilities, we state the problem, we look at table B, we sketch, and we unstandardize. So we're basically going backwards. We're flipping this. Okay, so we have, what height does a woman have to be in order to be in the 90th percentile? So this is basically asking you, we need to look up in the back of the book, where is 0.9000 going to be in the back of the book, so we can continue on with this formula. So we need to state the problem. Bam, here's number one. The heights of women in the United States vary accordingly to a normal distribution. And notice that we already are given the population mean as well as the standard deviation. So if the height in centimeters for women is 163.3 and the standard deviation is 6.5 centimeters, then we want to find out what, and this is our quick way of explaining this. We want to find the value that is that is within the 90th percentile. All right, so if we look in the back of the book, we are going to use table B for this. We are, again, working backwards, so we're not looking at the numbers on the outside because that is related to the standard deviation. We are finding the probability within that. So what does that look like? So if I look up, and I'm looking at all the numbers right here. I mean, it starts off very small and it gets bigger and bigger and bigger. So we are looking for the 90th percentile. So if I go all the way and I find what's closest to 0.9, which one would it be? It would be 0.8997 rather than 0.9015, because this is closer by 3 digits, whereas this is a little bit further. But then I look up where that is in part B, and that is 1.28, and you can't see it on this side, but we have 1.2 on this right here, but then that's not finished. We still need this part, 1.28. So our z-score at the 90th percentile is 1.28. Let's see what that looks like on the graph. So this area under the curve shows that at 1.28, this area is the 10th percentile, this area is the 90th percentile. So now we're just sketching it out. There's a smaller version of what we looked at. We had 1.28, voila. Okay, so now that we sketched it, what are we looking at here? We had the area of 0.9, or the 90th percentile. Well, this x is what we are trying to solve for. So we were able to find, we already had the mu, we already had the mean, we already had the standard deviation, but this is what we were able to find, and that is right here, which is 1.28. So if we calculate this, it is 163.3 plus the z-score times the standard deviation, and so we have 171.62. So the result of this is a woman that is at 1.71.62 centimeters tall is taller than 90% of the population. So the 90th percentile is at 171.62 centimeters. Okay, here's another example. We want to know what the gestational length is for less than 97.5% of all gestations. Whereas the previous example, we looked at the 90th percentile, we're looking at now the 2.5 percentile of this. And to find that in the back of the book, you're not going to actually find a 0.275. I'm sorry, yes, you will. But what we're looking at is, rather than looking at the high number of 0.975, we're looking at the smaller number here. So if we were to look up and try to find, it's going to be in the negative standard deviation side, whereas the previous was in the greater than the mean. We're looking at less than the mean, much less. And what do we find? We find that at 0.025, it is, as a z-score, negative 1.96. Oh, okay, I took another one. All right, so if we were to sketch that, we're looking at this tiny little spot right here, 1.96. So again, we are reversing the normal z-score formula, which is z over x minus the average over the standard deviation. That right here is the exact same thing as this, except we flipped it because we don't know what x is. So we have the 39, and we looked up our z-score right here, and that's going to be found right here. Whoop. And then our standard deviation of 2 weeks. So it's 35. So what is this saying? It is that the 2.5th percentile gestation is 35 weeks, because what we found out is just this tiny little amount right here. That's only going to be 2.5 of the normal less than 35 weeks is going to be at that 2.5. Sorry, I'm very tired. All right, we'll give it a shot. We'll give some practice. With normal probabilities, QQ plots are an excellent way to look at it visually. We will practice just popping these up in SPSS. Here is a positive skew, and this is a leptokurtic distribution, and from that, we're done ski.